This is geometry lesson 12.3. We're going to be looking at similar figures. So the big idea says by composing size transformations and reflections, similar figures are created. So in 12.1 and 2, we looked at size transformations and we looked at the ratios and the proportions we could set up between those two different shapes after a size proportion. And so today we're going to kind of define what that actually is, what that means. And we're going to call those similar figures. So we're going to come up here with a precise definition for similar figures. So under a size transformation, figures and their images seem to have the same shape. So think about that, what that means. If we enlarge something or shrink it, it still appears to be the same shape. It's just a different size. So under any definition, these figures should be similar. We know what that word just in general in the English language means, similar. So in math specifically, it's going to be the same shape, either smaller in size, larger in size, but in proportion. We know that when we perform an isometry, which we haven't talked about in a little bit, but those are reflections, rotations, translations, or glide reflections. They're all combinations of reflections. We know that the shape does not change size, right? If we flip it, if we rotate it, if we just move it, slide it and flip it, right? It doesn't change size, and it definitely doesn't change the shape. It still looks the same. It may be oriented differently, but it's still the same shape. It's not going to go from a triangle to a pentagon or something like that. So the precise definition of similar figures kind of wraps this all up. So here we go. So two figures, we're going to call them F and G here in the definition, are similar, which is going to be written like this. So we want to definitely know what those symbols mean, right? So that little squiggle, which we used to put on top of the equal sign to say congruent, if it's just the squiggle by itself, it means that they are similar. So they are similar if and only if there's a composite, which remember means there's just more than one, size transformation and reflection mapping F onto G. So we started with F. There's either been size transformations or reflections, multiple, or maybe just one. If that's true, we can say that these are similar, and we'll talk about what that means, what we're allowed to assume based on that information. So if you look at the picture here, we've got a bunch of different triangles. We started out with ABC, but ABC, PQR, SQT, and XYZ are all similar. So it's the same triangle. It's either just undergone a size transformation or some kind of reflection, rotation, etc. All right, so if you look from ABC to PQR, they're telling you that that's a size change from ABC with center O, and they're actually going to give you the magnitude here of 1.8. So we started here, and then from center O, right, each one of these points was extended 1.8 in terms of magnitude away from center O. So whatever this measurement was of A, we times it by 1.8 and then put P out there. Same thing for C and B, and then that created this enlarged version of ABC. So these are similar because this is just a size change. Then we have SQT, which is a rotation of this one at Q. So notice Q hasn't moved, right? But we've rotated each one of these around Q. Q has stayed put. That's the center of the rotation. So the size doesn't change, the shape doesn't change. They are still similar. So these are similar to each other, which means all three of these are similar to each other. And then finally, XYZ is a size change from here to here from M. So point Q, if you measured and you drew a straight line to M, you multiplied that distance by 2/3, it shrinks to here. You do that for all 3 points, and we end up with a size change here of 2/3. So it has shrunk, but it is still similar. It's the same triangle. The ratio of the sides is going to all be the same. All right, and so we can say that those are similar. And so, again, this is all about defining this. If all that's happened is size transformations and reflections, then we know that all of these triangles are similar. So down to the bottom, again, we already kind of touched on this. That little squiggle symbol is read similar to. If you look at the example here on the right, we started with MELON, so melon. It's undergone a size transformation of 1.7. So let's get used to seeing that notation again. MELON is in parentheses. That means that's what's undergoing the transformation. S is for size transformation. 1.7 is your magnitude. So each one of these points, the vertices of this shape, the measurement from A has increased by a factor of 1.7. So however far E was from A, we multiplied that distance by 1.7 and put R now that far away from A on that same line. And so then not only does it move away from A because we are increasing that number when we multiply by 1.7, we're also enlarging the shape altogether. So it's not just moving away from A, it's getting bigger by a factor of 1.7. If you measured all these side lengths here, the actual lengths have also increased by a factor of 1.7. So what we can say is, because this is just a size transformation, is that melon is similar to fruit, and we're going to talk about all the things that we are now allowed to assume if they are similar. We know something about the angles, we know something about the side lengths. But what we would say is, if we saw this notation here, we can say that pentagon melon is similar to pentagon fruit. That's how you would read this. And sometimes you just read the letters. MELON is similar to FRUIT, but obviously when they come up with little words like that, you can just read it. All right, so here's one very important point, and we're going to touch on this a lot on the back. Just like with congruent figures, if I wrote this is congruent to this, the corresponding vertices of your similar figures are written in corresponding order, meaning if this is similar to this, I know whatever M was in this first picture, it's going to correspond to F, right? I started with M. The new vertice that matches it after the size transformation is F. So just by looking at my similarity statement here, much like a congruent statement, the letters will match up and tell you, okay, this was M, now it's F. This was N, it matches T. N became T. And even the side lengths will as well. So EL, if you look, EL should match RU because it's the second and third letter. If I find them in the picture, EL is going to match RU. That makes sense. So sometimes when the pictures get complicated, you can always go back to the similarity statement to match up the vertices, match up the side lengths. All right, to the back. All right, so we're going to take this one step further now, looking at the definition of a similarity transformation. So it's really just, again, continuing to define things. So any transformation that maintains all the things that we're going to talk about in the similar figures theorem would be a similarity transformation. And again, that comes from size transformations and reflections. So they're all encompassing here. If you think about a reflection, right, we're not changing the size. So we've talked about A, B, C, D being maintained when we reflect things. If we have a size transformation, 3 of those 4 things we talked about in the last section will be maintained, but distance is not, because it's growing or it's shrinking. So clearly distance is changing. So that is not going to be preserved. But under a reflection, all of this is preserved. The shape has not changed size under a reflection. And so you actually have congruent shapes. That's true for all reflections, isometries. But they are still similar. The main thing that we want to understand between two similar figures is that their sides are in proportion. So if it's only a reflection and they're actually congruent, they are similar. The proportion is just 1 to 1. The size hasn't changed. So a 1 to 1 is still similar. Whereas if I undergo a size transformation, like if it doubles, it's now in a 2 to 1. Or if it's shrunk by a third, it's a 1 to 3 ratio. All right, so they're always going to be in proportion to each other with a similar ratio for all of the sides. And it can be 1 to 1. So even if it doesn't change size, they can still be considered similar. So congruent and similar will match up sometimes, but under a size transformation, the size is obviously changed, but they can still be similar. So here's the most important part, similar figures theorem. Corresponding angles are congruent, right? Angles are not changing. Angle measure is preserved whether we reflect something or we change the size. The side lengths get bigger, but the angles stay the same. That's very important. We're going to use that a lot moving forward. And then corresponding lengths are proportional. They could be the same size. They could be in proportion 1 to 1. But if all of the side lengths change by a factor of 10, they're all 10 times bigger, 10 times smaller, whatever it is. As long as they're proportional, then they are similar. Okay, so a lot of defining things. Let's now actually kind of get into some work. So we take a look at this first picture. Let's break down the notation again. In the figure at the right, we have a composite transformation here. We have two things happening. So CARP is in parentheses, meaning it's happening to that. So that's your first shape. We started with CARP. That was the original. I know that because it's inside the parentheses. Remember that the first thing that's attached to parentheses, that's what's happening first. And then we've got this showing that there's a composite. There's another transformation happening. That happens second. So the first thing that happened to carp is that it underwent a size transformation of 1.8, which means this is the second shape. So we went from here to here. It did not just move, it got bigger by a factor of 1.8. So if we connected C to the center O, that distance right there was multiplied by 1.8, and then the new point was put on that line, that new distance away. So CARP grew by a factor of 1.8 with center O, and then it was reflected over line M. So the little R means reflection. Over line M, it flipped over. S means size transformation. And the center is O. We already touched on that. So letter A. What is the justification? And yes, we will eventually start having to prove these things. What is the justification for the statement that says CARP, the original shape, is similar to fish, this one right here? Are they similar? Are they in proportion? And do all of their angles match? And we can say yes. They're already telling you it's yes, but what's the justification? How do you know that? And you say it is a composite, which means there was more than one, of, and remember back to the definitions here, if things are similar, they must have only undergone size transformations or reflections. And remember, rotations and translations are actually composites of reflections, so those would count as well. So this is a composite of a size transformation and a reflection. So that's how we know these are similar. The only thing that's happened to it is it's changed size, and it's been reflected. So therefore, I know that these are similar to each other. And if they're similar, that means all the angles are equal to each other or congruent, and the corresponding lengths are in proportion. Not the same size necessarily, but every single length has been increased by the same factor. All right, letter B. If angle P is 82, so this one right here, which angle in fish also has to have a measure of 82? So you could try and follow it along, right? P, if we underwent that size change, became R, and then if I reflected R over M, it ended up here, so it would be H. But very often the pictures can be a little too complicated to follow, and so you always want to just go back to your notation here and just match up the angle. P was in the last spot of carp, and so it's going to match angle H in the final transformation here. So yes, we followed in the picture and we saw P became R and then became H. So those are the same angle, and angle measure does not change. So those would both be 82 degrees. But we can also always go back here, even if we didn't have the picture. And if they told you P was 82, I know the matching corresponding angle is going to be sitting in the same position. So H, angle H equals 82. All right, what about side lengths? If RP, so in the picture right here, this length right here, if that was 6 in the original, what length in the new shape can be determined, and what is it? It's not going to be 6, right? We have changed the size, but it's going to all be in proportion, so we can figure out what the new side length is going to equal. But first we need to figure out which one it is. So if I look at the notation, RP is the second and the third, the third and the fourth letter in the original carp. And so that's going to match the same ones, S and H. So if I come over here, this is the side that's going to be in proportion with RP. And you can kind of follow it again through the picture. Size transformation, it just got bigger. RP became this length right here. And then when we reflected it over line M, it ended up here. So you can follow it in the picture, but you can also find it in the notation. RP is going to match SH. If it was 6, it's only undergone one size transformation. It was multiplied by 1.8. So all we're going to do is 6 times 1.8, and that is going to give us that new distance right there. So 6 times 1.8 is 10.8. So, and we should go ahead and write the actual letters there. We want to make sure it's in the same order. So instead of saying HS, if we started with RP, it's going to match S. H equals 10.8. All right, and then the last thing we want to look at is kind of just some more of the vocabulary and words that you're going to see, and just want to make sure that we're not thrown off by them. So we're going to talk about the ratio of similitude. That's a hard word to say. I don't like that word, but it's talking about things being similar, obviously. So the ratio of a length in an image to the corresponding length in a similar pre-image, a lot of jargon right there, is called the ratio of similitude. So again, the ratio of the length in an image, so that's the new shape, to the corresponding length in a pre-image. So basically you have a new shape, the image, the matching length of a side, that ratio that we come up with, like, oh, it's doubled, it's in a 2-to-1, or it's tripled, it's in a 3-to-1, or it's shrunk and it's in a 1-to-5, whatever it is. That ratio that we're coming up with, 2-to-1, 3-to-1, 1-to-5, that's called the ratio of similitude, and it's telling you basically the factor that something is increasing by or decreasing by. In many applications, which means many times, the ratio of the similitude will be called scale factor, and I like that a lot better. It's easier to say and it makes more sense because we're using the word factor there, and factor tells you it's increasing by times 3, times 4, whatever it is. So these two things mean the same thing. You can use either term. All right, so if you see scale factor and you see ratio of similitude, we need to know that it's not asking you anything different. It means the same thing. All right, so unless otherwise specified, when two shapes are similar with a ratio of similitude k, the lengths in G divided by the corresponding lengths of F will equal k. So just reading that sentence, it sounds confusing. But basically, if we kind of skip down to the picture over here, if we have these corresponding lengths and we know that these are similar, in this shape they will be similar, so we're kind of already jumping into this question right here. The ratio of similitude is going to be represented by k. If you think about where we've seen that before, in this notation, k would go here. So a third word that kind of matches all of these is the magnitude of the size transformation. So ratio of similitude, the scale factor, the magnitude of the size transformation, they all mean the same thing. So we just got to kind of put that vocabulary to bed and not worry about it. It all means the same thing. But where does that ratio come from? If you're given the picture, how do you come up with the ratio? All right. So it is the ratio of the lengths in G, which is the second figure. All right, whatever it is here, F was similar to G. So if this was F, this would be G. It's just the ratio of the corresponding sides. So remember that a ratio is just a quotient or a comparison of two numbers. So right here, they're similar. We're going to find the scale factor. Find the ratio of similitude. Find the scale factor means the same thing. From this one to this one, it says from the smaller figure to the larger figure. All right, so F is similar to G. So what happened to the sides? We're comparing 4 to 24. This is a ratio. If they say find a ratio, this is a ratio. Remember that you can write it 4 to 24 like this. You can write it 4 to 24 like this. Notice that it's not 24 to 4. That would be going the other direction. That would be if we started with this as F and then it became G. They're going to be similar, which means all of the angles are the same, and it also means that all of the sides are in proportion. So whenever we have one of these, and we're going to call this the scale factor, we're going to call it the ratio of similitude, we're going to call it the magnitude of the size transformation, we're going to want to simplify this. Okay, so most of you can do that just right there in your head. You can look at it and say, oh, I times this by 6, or I divided it by 6 to shrink it. But if you don't see that, you can always just punch this in. 4 over 24 is 1/6. If you're going the other direction, you would have had 24 over 4, which is 6. But again, you need to be consistent. Which way are we going? We started with F, we went to G. It shrunk, so we're expressing this as a number less than 1, or a ratio, quotient, less than 1. So this would equal 1/6, which you could write as 1/6. All right, and we're going to go ahead and we're going to find the missing length. Find the missing length. So we're missing this one. It's obviously going to be bigger than the corresponding side that it matches up with. So 24 compares to 4, the same way that this compares to 6. So you can go ahead and just use the scale factor here. I know that 24 divided by 6, 1/6 of it is 4. So if I divide this one by 6, what's it going to match up with here? And I can also go back the other direction. 4 times 6 gave me 24. So 6 times 6 is going to give me 36. All right, so you can use the scale factor. You can use the ratio of similitude to go this direction if you want, times 6, or to think backwards, something divided by 6 got me 6 because this divided by or times 1/6 relates it better. But remember, timesing by 1/6 is like dividing by 6, going that direction. And also remember, you can always set up a proportion with these ratios. You can say 24 compares to 4, the same way that x compares to 6. And then you can go ahead and multiply 24 times 6. You're going to get, oops. So 24 times 6, if we cross multiply right here, is 144. It's going to equal 4x here. And then when you divide by 4, x equals 36. So you can solve this by setting up a proportion, or you can just look directly at the scale factor, the ratio of similitude, and just use that number as a product to get there.